So far we've looked at rate laws that relate speed or rate to concentration. And then we've used a rate constant to go between the two. And so we've been able to relate rate with concentration. In this video, we'll take the rate law equations or the rate law expressions of three very popular rate expressions or rate laws, and we'll perform a calculus operation to those. And then when we do that, we'll get some new equations as our quote answers. And then we'll be able to use those equations to relate the rate or the change in concentration with time. Notice time is not in this equation right here. We have concentration and we have rate, which is molarity per second, but there's not T for time. And so once we perform that operation, we'll be able to solve for time or use time to find out what the concentrations are or the amounts are at particular times in the reaction. So far we've learned rate, speed, molarity per second. K is the rate constant. Temperature changes this rate constant, by the way, and so we always assume temperature is constant until it's not. And then a catalyst also changes K, and that's how it offers an alternate pathway. These are concentrations right here, and then these, of course, are the orders right here, and you add the orders together to get the overall order. So with calculus, we can manipulate these equations to relate concentration and time. And you have a notes page, looks like this guy right here, that we're going to use to organize three different rate laws and then perform the calculus operation of integration on those three different rate laws. We're going to look at a zeroth order. So imagine it's this equation right here, and the x is a 0. A first order, remember imagine it's this equation, but the x is a 1. And a second order, so imagine it's this equation, but the x is a 2. So we're only going to look at those three because those are the three probably most popular as far as being seen in nature or just used. So anyway, your book talks about first order reactions, and it actually goes through a little bit of the derivation right here. And for you calculus folks, you can see that it does a tiny bit of it right here. And then your textbook talks after that about second order and zeroth orders. I've organized them for you in a sheet right here, and we're going to take the notes right in each spot right here to talk about the equations and the relationships for all three. So take a moment right now and make sure that you've got this down, and then make sure that you've got this sheet out to write the notes on, and then I'm going to zoom in on this. And we won't really look at the textbook very much because we're just going to copy things down from the textbook. Maybe there'll be a time when we go back to it, but mostly we're going to take the notes right here, and that'll be your organizational piece. All right, so let's scoot this out of the way. Let's get this guy out of the way right here, and let's zoom in on this notes guide right here for three different change in concentration with time integrated rate laws. So first of all, zero order rate law. So a zero order would have the rate equation that you already know, where rate is equal to K, and then for this we'll always use the equation A goes to some kind of products. And so it would be A to the 0 power. And so since it's anything to the 0 power is 1, technically the equation is rate is equal to K. Sometimes you'll see the rate law or the rate equation or the rate expression written like that. So when you perform integration on this equation, then you get an equation that looks like this. The concentration of A original minus the concentration of A at some particular time is equal to K times T. This little 0 right here means original. So like when you're starting the reaction, this T stands here for at a given time. This K right here is the same thing as in the rate law expression. It's the rate constant right here and has units. And then T, of course, stands for time, and time can be measured in seconds, hours, days, weeks, years, depending on how fast the reaction is and what we want to measure it in. Now, an interesting time in all of these rate law equations is when we're at half the original amount of what we started with, and they give that a fancy name. They call it the half amount, but they do it at what time that is, so they call it the half-life. And so the half-life equation for this is T, and then they put a little 1/2 down here indicating that it's 1/2 the time, is equal to the original concentration of the reactant divided by 2K. Now, if we take this equation and we manipulate it just a little bit, and that's why I saved some space right down here, and you can write it in either space depending on how much room you used, we can put this in terms of A at a particular time is equal to, and then we're going to bring this to the other side over here, and that is equal to negative KT plus A original. I distributed the negative through, and I want the negative to be right there because now this equation is in y equals mx plus b format, which you've all seen from math class before. And so now you know that this is the vertical axis right here. This is the horizontal axis right here. And then m is the slope. And so notice that the rate constant is the slope. And so graphically, you could say that concentration goes on the vertical axis right here. Time goes on the horizontal axis right here. And then notice there's a negative sign right here. So the slope will be negative for a zero order reaction. Notice it's concentration versus time. And then what is K for the equation? Well, K, as we just noticed, K is the slope. Slope of the line right here. See, K right here is the slope, mx plus b. And notice that it's negative, because it's going in this direction. And then the units for the slope would be, slope as you know is equal to rise divided by run, or y divided by x. And so that would be molarity on the vertical axis, and then time on the horizontal axis. So I'll put seconds right there because that's just a unit of time, but it could be hours, days, weeks, years, something like that. And so if you want to be more general about it, you could say it would be a concentration divided by time. And sometimes you don't see concentration, sometimes you'll see pressure, so it could be atmospheres. Sometimes you'll see like particles or amounts, and so they'll confuse you with that, and they won't always have molarity. All right, that's the first one. Second one, this is a first order equation, so now it's K times A, and then this would be to the first power right here. You can put a little 1 up there if you really want to. Otherwise, just know that there's a 1 there. And then when this equation undergoes integration, then you end up with ln, yep, natural log, ladies and gentlemen, of A original minus natural log of A at a particular time is equal to KT. So notice it takes the similar format right here, but now we have natural log. Yeah, it's the kind of log that you find out in your backyard because it's in nature. Yep. So anyway, then you can take this and you can rearrange it just like we did here. And so you can have the natural log of A at some time is equal to negative KT plus the natural log of A original. And this then is that same format of y equals mx plus b. And so I'll skip right down here and we'll get to the graphical part of this one. The natural log of the concentration goes on the vertical axis. So notice how this one was concentration, this one's natural log of concentration. And then time, once again, is your x-axis right here. And then notice it's got a negative slope. And then K is the slope. So rise divided by run, once again. And so K tells you what the slope is. And so sometime, to be really tricky, they'll give you a graph and they'll say, this is the natural log of concentration versus time. What is the rate constant for this reaction? Well, now you got to go back to your 8th grade algebra, and you got to be like, oh, I got to find the slope of that line. So you got to do like rise divided by run to find that. So maybe write yourself a little note and say, self, watch out, I might have to find slope sometime. Let's see, and then the units on here would be rise divided by run. So this would be natural log of molarity, and since the natural log is a exponent, exponents don't have units, so it would just be 1 over a unit of time. So 1 over seconds, or 1 over time. And so to be tricky, of course, what they'll do is they'll put it time to the negative 1 power, you know, rather than write it as a fraction. Just like here, they do concentration times time to the negative 1 power as well. All right, getting back here to the half-life equation. The half-life equation for the first order process is actually one that you may have learned in Algebra 2 or maybe in pre-calc. And so this is time 1/2 is equal to the natural log of 2 divided by k. And so natural log of 2 is just a number, and then you can notice that the half-life is only dependent on k. Interesting. It's independent of the initial concentration, whereas here you can see it depends on what the initial concentration is. This, if you took Algebra 2 or maybe pre-calc, you used these types of equations, maybe in a little bit different format, to do radioactive decay. And all radioactive decay processes are first order processes, and so they'd use these equations right here. All right, last one. Rate is equal to k, and now we're at a, and it's going to be squared, right, because it's a second order process. When this undergoes integration, we now end up with 1 over the concentration of A minus 1 over the concentration of A0 or A original or A naught. That O, remember, means original, like original recipe. And then that's equal to K, K times T. Do you guys even know what original recipe is? It's Kentucky Fried Chicken. Yeah. Okay. So you could rearrange this then, and then it would be 1 over A is equal to, and then it's positive KT on this time, and then that's plus the 1 over A original. And so we end up this time with a positive slope for this one. So when you graph it, we end up with 1 over A original, or just A right here. It's 1 over A on the vertical axis, and then time, once again, on the horizontal axis. But this time you get a positive slope. It's your only one with a positive slope, and the slope, of course, is K, because we're in Y equals mx plus B format right here. And then the half-life for this guy turns out to be T1/2 is equal to 1 over A original times K. So you can see that the original amount does affect the half-life right here. Both the first 0th and the second order, you have the original amount affecting how much time it takes to get to half the amount. Whereas in the first order, notice it's independent of that amount. Let's see. Lastly, right here, K, of course, is the slope once again. And then the units for the slope would be, so it'd be 1 over molarity over seconds. And so you remember this could also be written as seconds over 1, and then you can multiply by the reciprocal. So then you end up with 1 over molarity times seconds, or the fancy way to write that would be molarity times seconds. So if you want to write it in general, you'd just say concentration to the negative 1 power times time to the negative 1 power. All right, so hopefully I didn't make too many mistakes on translating this for you. There's always a possibility that I missed something. I probably lost a negative somewhere in here, maybe 2 or 3 times. But we'll clean it up when we go through it in class as well. But these are the 0, first, and second order equations. I'll triple check these before we go on to 3 example problems. I'll have 3 videos in a row here where we do one for 0 order example problems using these equations, one for a first order, and then one for a second order as well. All right, good luck with your integrated rate laws.